Swayam Prabha. Digital India. Educated India.
Now in the next about half an hour, I am going to show that Hamiltonicity problem is these problems are also NP complete, but I am just saying it is NP hard. Okay. So, first if you want to show some problem is NP hard, what do you have to do? Reduce some known NP hard problem to this problem. This is okay, very important. Don't reduce this problem to that problem, then you are not showing anything. You have to take a known NP hard problem and reduce to this. Okay. Now there are lots of choices now, right? We have already shown SAT, vertex cover, click, independent set. So we have to pick one of them and reduce to this. Now which one do you choose? Not immediately obvious usually, right? When you look at click and independent set, they look similar. Maybe there's something shows up, take the complement and it gives you. Whereas if I want to show some Hamiltonicity problem or any other problem you want to show NP hard, it's usually not very easy. Where do I start? Which problem to start from? Okay. You just gain by experience anyway. So here is some high level intuition. I'm going to reduce from vertex cover problem. Okay. Why? Somehow both are covering problems. Okay, that's the best explanation I can give. Okay, since I know it, I can tell you this. But if I have to try and prove something is NP hard, I don't know where I will start. Right? Because vertex cover is trying to cover all edges. Hamiltonian question is trying to cover all vertices by a cycle, right? So, but beyond that, it is magic how they came up with it, right? So it's ingenious construction. So what do we have to do? Given a graph, so input here is G and you are asking for a vertex cover of size K, a subset of vertices that cover all edges, and I am going to construct a G prime. There is no K or anything here. With what property I want? What is the property I want in this reduction? G has a vertex cover of size K if and only if G dash is Hamiltonian. Okay. So somehow, if you give me K vertices to cover all edges, I'm going to use these K vertices, run through all, it's the edges incident on each of the K vertices and argue that all edges are covered here, right? We know that. I'm going to somehow create some gadget for each edge here and then say that if you give me K vertices, I can walk through these K vertices and cover all the gadgets corresponding to the edges, and that will give me a Hamiltonian cycle. Okay. So I'll start giving by an example. We'll do the reduction and then we'll lift it to a general proof. So let's say I have this graph. I can only give a simple graph because it's very hard to draw otherwise. So here is my graph G and I'm interested in a vertex cover of size 2 in this graph. And we want to construct some gadget here, G prime here, such that this has two sized vertex cover if and only if this graph is Hamiltonian. Okay. So the way we will do it is for every edge, we are going to construct some little gadget. So let me just see how the gadget will look like. So there is a gadget for AB, there is a gadget for BC, is the gadget for the edge AC and the gadget for the edge CD. These are the 4 edges here. I will have these 4 gadgets. In addition, since K is 2 here, I am going to have this. Let's dot here S1 and S2, 2 selector vertices. In general, if you have a K here, it will be S1, S2 up to Sk. This is how an edge gadget will look like. Okay, and a gadget is simply a graph corresponding to the edge AB. Okay, I can number them, but let's see. So similarly, exactly a copy of this for BC, copy of this for this edge, copy of this for this edge, and then these guys are adjacent outside. Okay, now let's look at any Hamiltonian cycle of. So I am going to fill up. So these are the vertices of the graph, right? S1, S2, and this is 6 plus 6, 12 for each edge, and that's my entire vertex set. I am going to fill up my edge set. Okay, but before I do that, I want to give you an intuition of why I am going to construct it this way. Let's look at a Hamiltonian cycle in this graph and see how it would visit this particular gadget. Okay, so it enters, let's say, from here, the Hamiltonian cycle. Where can it go? After it comes here, it has to go to this vertex. There is no other choice. Okay, and after coming here, there is no other choice. It has to go to this vertex. Right now, it has a choice. Where can it go? It can go here or it can come back here. But if it decided to come back here, and if it uses some edge like this, then these vertices can never be covered, because this is a degree 2 vertex. Okay. So what is my claim? The claim is that the Hamiltonian cycle of this graph, it exists. It might just enter here and come out here without visiting edges of these vertices. This is one possibility. What is the other possibility? It might just come here and go here, come back here, and go and come back out here. So it will enter and exit through the same side. Either it will visit both side of the things and come back, or it will come out only through this. This is the only way any Hamiltonian cycle will visit this gadget. Why? Because these vertices are degree 2 vertices. So if you come here and get somewhere else, and this vertex will never get visited. Okay, this is important. So just pay attention to this again one more time, and after that you have to think about it yourself. So the way I have constructed this gadget, because there are remaining edges I need to draw, but they are all going only out of these boundary vertices, right? So any Hamiltonian cycle for this graph, if it enters this gadget through this vertex, it will, first of all, it will get out only through this vertex. Because if it just goes somewhere else and gets out here, then these vertices can never be visited, because we are talking about a Hamiltonian cycle. So every vertex must be visited, and I have degree 2 vertices, they can never be visited if you skip them in this process. So if they get in, they should get out only through this end of that vertex. But there are two choices: either it visits this entire thing and come out, or it just comes out this way. Okay, this is the first thing you should get convinced about it. That's all is required. Then rest are all easy after that. Okay, so now let me just fill up the remaining graph with the edges of the graphs. So this BC also has this kind of a gadget. So BC also has something like this with this kind of an edge. Similarly, this. Okay, now I have to tell you how the edges between S1 and S2 are and how these guys are connected. Okay, so think of this as Okay, the way I'm going to label them is AB1, AB2, AB6, and this would be BA1, BA2, BA6. Similarly, this would be BC1 and this will be CB1 and 6, and this is how the vertices are labeled. So what, again, let me just go back to the intuition. What am I trying to do, right? Suppose this graph has a vertex cover of size 2. Is there a vertex cover of size 2 here? What are the vertices? A and C, right? And what do I want now? Use this AC to somehow get a Hamiltonian cycle here. Okay, how do I get? So, and then based on that, I'll fill up the graph. So, I'll start from S1 and go to A's first neighbor. Okay, so basically, order the edges incident on A. Let's say AB is the first edge and AC is the second edge. So, I will go to this AB gadget and visit them somehow. After finishing that, I will go to the A's other neighbor, which is AC gadget, visit them, and then I come back to C and visit all the neighbors of C, CB gadget, CA gadget, CD gadget, and I'll be done, completely finishing up the entire vertex set and get a Hamiltonian cycle. Okay. So, to enable that to happen, what am I going to do? I am going to add S1 to all these 1 edges. Okay, it's an undirected graph, so ignore the direction for the moment. S1 is adjacent to all these 1 vertices. Yeah. Similarly, S2 is also actually adjacent to, and these end vertices, the end vertices here are adjacent to, again to S1 and S2, plus in addition I am going to have an edge from the end vertex to the next copy of that edge. So, AB1 to AB6 will have something to AC. So, not this edge, it will have something to AC1, and then AC6 will have, those are only 2 edges here. So, I will connect back to S2. The CB1 or BA1 will have BA1, BA2, BC, BA6. The last of this will go to the next edge incident on B, which is BC. So, I will have this connecting to the BC gadget, and at the end of it B is over. So, it will go back to S2, and from C it will have, there will be something corresponding to CA1, CB and CD. So, after all of this I will go back to here, and then I will go back to CD and then go back to S2. Okay. It is a very subtle construction. I am just trying to give you the high level ideas. Formal proof is there in the books, you can check. Okay. So, if you have a vertex cover of size 2 here, then my Hamiltonian cycle will look like this. I will start with S1, go to the first vertex in the vertex cover and go to the first edge incident on that vertex. Right, arbitrarily order the edges incident on the vertices and go to the first edge and go to that first edge gadget and visit them, visit it completely and come back, and then after that go to the second edge incident on that A and visit that and completely, and then come back to S2 and pick up the next vertex, finish those gadgets and come back. Okay. Now, I have a choice. When I look at the, let us say the AC edge, when I come here, I have a choice of either come back here and get out here or go back here and finish the whole thing. How do I exercise my choice? If you answer that, you will understand what I am saying, right. So, my goal is to run through all edges incident on these vertices. Since this is a vertex cover, that will cover all the edges, to visit all the edge gadgets starting from S1. Right. So, when I am visiting A's edges incident on A, I have a choice of AB and AC. Right. So, this edge gadget and this edge gadget. So, from S1 I will finish this and come back and go to the next one and come back to S2. Now, in each of them, I have a choice of visiting the other side also or not. How do I decide what to do? Well, it depends on whether the other endpoint is in the vertex cover or not, right? Because when I am visiting AC, I will finish, come back to my AS thing and come back here, or I can do this and come back here. Do I want to visit this or not? The choice I make based on is C is in the vertex cover. If C is in the vertex cover, then when I visit C, I will get here. If C is not, then I might go and grab those vertices also. Okay, and so if you have a vertex cover of size 2, then I will start from S1, go to the first vertex, let us say A, first edge incident on that 1, finish the whole thing, come back to the next edge, whatever that is, finish them and come back to S2, and then from S2 I go to the next vertex, finish all the edges and come back to Hamiltonian cycle. Okay. I just want to give you a reasonably complicated example, and that is why it is. It's quite a subtle involved construction, and the idea is because this is covering edges, so I am going to have some gadgets for edges and use the vertex cover to traverse the entire vertex set corresponding to all the edges. And the converse, the way you show is that if you have a Hamiltonian cycle, the Hamiltonian cycle should visit this S1 and S2, right, because it visits every vertex. So, I break up the cycle from S1 to S2, what does it visit? And we can argue that it must visit edges incident on one vertex. So, that vertex I will throw it into my vertex cover, and then from S2 to the other copy of S1 to complete the cycle, I am going to visit edges corresponding to another vertex, and those two vertices will form a vertex cover. Okay. I am sure I have successfully lost everyone, not surprising because it is a reasonably involved reduction, but hopefully you got some big picture ideas of how to do these reductions and what sort of gadgets you need to construct. The idea here was that there is exactly two ways to visit these 12 vertices in a Hamiltonian cycle. Okay, that's the main idea, and that's how this gadget was constructed with degree 2 vertices in between, so that either you go this way or you just go out and come back this way. Okay, so let's do relatively simpler, much simpler reduction now. And what do I want to show? Let's define another problem, the traveling salesperson problem, right? You would have all and what is the question? Well, what is the input? By the way, this reduction is there in Carmen's book. Okay, so you can try and read and understand it as well. Okay, so what is the traveling salesperson problem? You are given a graph. Let's say you are given a complete graph. With some capacities or distance from I am happy with integers, positive integers, so let us say n. Okay. And what is the question? Do you know? So, what is the traveling salesman problem? Vertex exactly once. Find the minimum cycle that visits every vertex exactly once. It is not a decision problem. So, how do you convert it into a decision problem? Yes. So, the input contains some k, not k length, but k distance, right? Does there exist a cycle that visits Okay. Every vertex and whose cost is or total distance is okay. First of all, I mean, for whatever we have learned so far, you should immediately see that this is hard. This is hard. This cannot be an easy problem. Why? Hamiltonian cycle, finding whether there is a Hamiltonian cycle itself is hard. But remember, this is a complete graph. There is always a Hamiltonian cycle. It's not a problem, right? So I've given you weights. So in general, if there is no, weight on an edge, put an infinity or something like that. So this is there is always a Hamiltonian cycle. So this is asking, is there a Hamiltonian cycle whose out of all the Hamiltonian cycles, is there one whose total cost is at most k? So if I want to show it's NP hard, you know the natural problem to reduce from, right? What problem? Hamiltonian cycle problem. You don't have to think very hard for this problem. So you want to reduce from Hamiltonian cycle, right? So we want to reduce Hamiltonian cycle to TSP. So first thing is to figure out which problem I am going to reduce from. The next important thing is to capture the input for each of these problems. That's very important, right? So for Hamiltonian cycle, what is the input? You are given a graph. That's all, right? An undirected graph, no weights, nothing. And for TSP, what is the input? G dash comma k, but this G dash is, there are weights on the edges. This is an additional thing, right? There is distances on the edges. So G dash is a complete graph. So you need both, right? So you want to translate, and with what property I want? What is the property I want in this reduction? G has a Hamiltonian cycle if and only if G prime has a Hamiltonian cycle with total distance at most k. So k is your choice, G prime is your choice, the distances are your choice. I am giving you, I want to solve the Hamiltonian cycle problem, here is a graph, and you claim you have an algorithm to solve the TSP, and how do I use that to solve my problem, right? You want to do this in polynomial time. Okay, so how do we do this reduction? So you are given an arbitrary undirected graph. First I have to make it complete. I have two jobs, right? I have to make it complete, and then I have to put some weights on the edges, and then in a way that this has a Hamiltonian cycle means that there is this Hamiltonian cycle of this weight, and k is also your choice. Since you are going to make it complete, remember G prime is going to have all kinds of Hamiltonian cycles, lots of Hamiltonian cycles, various weights. But can you control the weights so that, using k, if this gives you such a Hamiltonian cycle, then you will get your Hamiltonian cycle in the original graph. So how do we want to put the weights? And there is a natural choice for this distance function. We did it for network flows. There are no weights, right? Look at the picture. You have an unweighted graph. There are no weights. Now your job is to put weights. What's a natural choice for putting weights? If graph has some edges, graph has no edges, and somehow we want to show that if there is no edge, then that is like a costly distance, right? So what's a natural choice? I don't know that. You made a very good point. You cannot assume that it has a Hamiltonian cycle and do my construction, right? To start with, you are only given a graph. I have to do my construction in a way that S will go to S, no will go to no. Okay, which are not present? Infinity. Okay, here is a suggestion. So you are given a graph here. on n vertices. So, I am going to maintain the same number of vertices. So, what we are going to do is my G prime. So, G is on the same vertex set and H set, G prime is on the same vertex set, but I am going to make it complete. All edges are present. Now, I am going to, here are my choices for the distance. So, what the suggestion is that dij is equal to 1 for original edges of the graph. Otherwise, he suggests put a cost of infinity. Okay. Let us go back to my input. My input needs G prime, which needs weights and a k as well. So, you have to give me a k. What is k? N plus 1. Okay. And you are going to give me n plus 1. Yes. Right. What property do I want? This is the property I want. So, he has now given my construction and he had the following goal in mind to give the construction. So, now we have to prove this. G has a Hamiltonian cycle implies there is a Hamiltonian cycle with total distance at most n plus 1, because your k was n plus 1. And if there is a Hamiltonian cycle with total distance at most n plus 1, that must correspond to a Hamiltonian cycle in the original graph. Right? Is that true? And anybody wants to change the k? N. N is good enough, right? Because n is the number of edges in the graph, in the cycle. Right? So, the claim is, let us prove this. I mean, there is nothing to prove. G has a Hamiltonian cycle if and only if G prime has a Hamiltonian cycle with total distance right. So, what did we do? So, let us do an example. So, here is my I believe this graph does not have Hamiltonian cycle. So, here are my vertices and edges of the graph. So, what did we do? We filled up remaining edges, because I have to make it a complete graph. So, first thing he did was to give a weight distance of 1 to these edges. Anything which was in the original graph, we will give a distance of 1. For anything else, we will add that edge and give an infinity distance. Okay, right? There are all these edges missing. So, we have made it a complete graph. Okay. Now, the claim is, if G has a Hamiltonian cycle, what is the distance in my G prime of that Hamiltonian cycle? N, because you are using G's edges. So, use those edges. G's edges have distance 1, right. So, the Hamiltonian cycle distance will be n, right. Can you have a Hamiltonian cycle with distance less than n? No, because there are n vertices. So, the cycle should have n edges, and the way I have put the capacities, they are all 1. So, 1 or above. So, you cannot have a Hamiltonian cycle with capacity total distance less than n. So, if you have a Hamiltonian cycle, I have pulled the same Hamiltonian cycle in the graph, is also present in G prime, but with total distance n, right. But suppose G does not have a Hamiltonian cycle, right. G prime has many Hamiltonian cycles because it is a complete graph. But what can you say about the distance of any Hamiltonian cycle in G prime, right. So, G has Hamiltonian cycle implies G prime has a Hamiltonian cycle with distance n. There is nothing less than n possible anyway. And if G has no Hamiltonian cycle, implies any Hamiltonian cycle in G prime has, why? distance greater than n. Why? Because first of all, any Hamiltonian cycle has n edges. There are n vertices, so it should have n edges, right? Any Hamiltonian cycle has n edges. So take that n edges. Can all the weights be 1? No, because G did not have a Hamiltonian cycle, and only for edges of the original graph I gave a weight of 1, right? If everybody has weight 1, that would correspond to a Hamiltonian cycle in G. Since G did not have a Hamiltonian cycle, it must use Hamiltonian cycles exist in G prime clearly, but it must use these infinity edges, so the total distance will be strictly more than n. Okay. Now that we have done it, can you reverse engineer? Do we really need infinity for a distance? What distance is enough? Just 2 is enough, right? Just give a distance of 2 for non-edges and 1 for edges. Because there are n edges, at least one edge has distance 2 because it's a non-edge, so total will be greater than n. So even this is enough. Okay. So this shows that the TSP problem is NP hard, but lo and behold, we have shown something even stronger. We said the traveling salesman problem is NP hard even if the distances are 1 and 2. Now this is a stronger statement because you said that even if the distances are restricted to something, it's a hard problem. It's like the 3 SAT is NP hard. The general SAT was NP hard, but even if you restrict it to 3, if you show it's NP hard, then it's a stronger result because you're saying even if the distances are 1 and 2, it's NP hard. Okay, so just to summarize, if I have to show some problem is, so all these problems are also NP complete. I am not emphasizing that, but how do you show something is NP complete? It's NP hard and the problem is also in NP. So the S answer has a polynomial time verifiable certificate, right? So in this case, a Hamiltonian cycle with the total distance at most k would be a certificate which can be verified. You just check that these edges are there and the total distance is at most k. To show some problem is NP hard, you pick a known NP hard problem. So first task is to identify, what does this problem look like? Is it a covering problem? Is it like Hamiltonianicity? Is it like this? That kind of thing, right? So there are some problems in the problem sheet you will see and you have to connect to it, and the more problems you prove NP hard, you have that much more choices of problems to start from, right? So first thing is to identify which problem it looks like. And then you have to give a reduction from that problem to this problem. Okay. So next step is to identify what the input for that problem is and input for this problem is, right? So we said Hamiltonian cycle, input is G, for TSP is G prime and K, it's a weighted graph and all that. Then your task is to come up with the transformation or a reduction, a polynomial time algorithm function which transforms an instance like this to an instance this, with the property that S instances go to S instances, no goes to no. So that an algorithm for this can be used to solve this problem.